The unfolding influence, origami's pivotal role in modern engineering. In the realm of modern engineering, the ancient art of origami has emerged as a significant influence, offering not just an aesthetic pleasure but also a plethora of practical applications. This traditional Japanese practice of paper folding, once primarily associated with craft and leisure, has transcended its artistic boundaries to inspire innovations in fields as diverse as aerospace, architecture, robotics, and biomedical engineering. The core principle of origami, transforming a flat sheet of material into a complex, three-dimensional structure through folding, aligns remarkably well with various engineering challenges, particularly those involving space optimization and material efficiency. At its essence, origami teaches the art of maximizing space and structure from minimal material, a concept highly coveted in aerospace engineering. The need for compactness during launch versus expansiveness in deployment makes origami principles invaluable. NASA, for instance, has harnessed origami concepts in the design of solar panels and space telescopes. The James Webb Space Telescope, a marvel of modern astronomy, employs a sunshield that unfurls in space, a mechanism directly inspired by origami. Similarly, the deployment of solar sails, essential for powering spacecraft, draws from origami techniques to unfold large structures from compact stowage. The field of architecture also significantly benefits from origami principles, particularly in creating structures that are not only aesthetically unique but also structurally sound and material efficient. The ability of origami to manipulate form and space without cutting or adding material resonates with sustainable architectural design, leading to innovative buildings that are both functional and visually captivating. For instance, the concept of foldable emergency shelters, which can be rapidly deployed in disaster-hit areas, is a direct application of origami in providing immediate, practical solutions to pressing human needs. In robotics, origami inspires the design of flexible, lightweight structures, paving the way for robots that can adapt to various terrains and tasks. The principle of using minimal material to achieve maximal functionality is crucial in robotics, where efficiency and adaptability are paramount. Origami has led to the development of origami robots that can fold themselves into complex shapes, allowing for a level of versatility and adaptability that is invaluable in navigating challenging environments or performing intricate tasks. The biomedical field, too, has embraced origami in developing stents, implants, and drug delivery systems. The concept of delivering compact devices that can then expand within the human body is inherently linked to origami principles. This approach minimizes the invasiveness of medical procedures and optimizes the functionality of biomedical devices. For instance, stents that can be inserted into the body in a compact form, and then expanded to support blood vessels draw directly from origami concepts. Despite its apparent simplicity, the mathematics and physics underlying origami are profoundly complex, involving principles of geometry, topology, and material science. Engineers and mathematicians collaborate to create models that not only predict folding patterns, but also optimize material characteristics to achieve desired functionalities. The interplay between theoretical understanding and practical application is at the heart of origami's integration into modern engineering, pushing the boundaries of what is achievable with foldable structures. Moreover, the advancement in computational tools has significantly propelled the integration of origami into engineering. Computational origami, an interdisciplinary field combining mathematics, computer science, and engineering, focuses on algorithmic and theoretical aspects of folding. Software tools capable of simulating folding patterns and structural behaviors under various conditions are instrumental in transforming origami from an art form into a powerful engineering tool. In conclusion, the influence of origami in modern engineering is profound and multifaceted. Its principles of space optimization, material efficiency, and aesthetic elegance have found resonance in a myriad of engineering applications. From the vastness of space to the intricacies of the human body, origami-inspired designs demonstrate not only the versatility and adaptability of this ancient art, but also its potential to continually inspire future innovations. As engineers and designers delve deeper into the complexities of origami, the fusion between this traditional art form and cutting-edge technology promises to unfold new realms of possibility, redefining the boundaries of modern engineering and design.